Imagine looking up at the night sky, tracing the familiar patterns of stars and constellations. But what if I told you that everything we think we know about the vast cosmos is only the tiniest fraction of the full picture? Beyond those shimmering points of light, beyond even our most powerful telescopes' reach, lie phenomena so strange, so mind-bending, that they challenge the very laws of physics as we understand them. The universe has always been full of secrets, but right now, in observatories and research centers around the world, scientists are uncovering discoveries that are rewriting textbooks and reshaping our cosmic perspective. These aren't just small updates. We're talking about monumental shifts in how we see space, time, and our place in it all. And today, we're going to explore 25 of these astonishing, newly discovered space phenomena, each one more incredible than the last. Think about it. For centuries, humanity gazed at the heavens with wonder, but also with limitation. We could only see what visible light revealed. Now, with advanced technology like the James Webb Space Telescope and gravitational wave detectors, we're peeling back layers of reality we never knew existed. From rogue planets drifting alone in the dark to black holes behaving in ways that defy explanation, the cosmos is proving to be far stranger and more magnificent than we ever dreamed. These discoveries aren't just for scientists in labs. They're for all of us, anyone who's ever felt a sense of awe under a starry sky or wondered what might be hiding in the depths of space. This journey is about tapping into that shared curiosity, that universal desire to explore the unknown and uncover truths that connect us to something larger than ourselves. So if you're ready to have your mind expanded and your imagination ignited, you're in the right place. We'll traverse cosmic mysteries that range from the beautifully bizarre to the utterly terrifying, each discovery opening new doors to understanding not just the universe but our own existence within it. This isn't just a list, it's an invitation to see the cosmos through new eyes, to witness in real time how humanity's quest for knowledge is revealing wonders beyond our wildest fantasies. Let's dive in together and explore what's truly out there. And we begin with a phenomenon so peculiar it earned itself a name straight out of a children's book, yet its true nature is anything but childish. It's known simply as the cow. Officially catalogued as a 2018 cow, this event was first spotted in June 2018 in a galaxy roughly 200 million light-years away. What made it stand out instantly was its almost absurd intensity. It wasn't just a little bright, it flared up to be nearly 10 times brighter than a typical supernova, and it did so with shocking speed, reaching its peak luminosity in a matter of just days, not weeks. For something of that colossal scale to happen so fast was completely unprecedented, sending astronomers around the world into a frantic scramble for explanations. The initial assumption was a supernova, the violent death of a massive star, but the cow broke all the rules. A normal supernova's brightness is sustained for some time by the radioactive decay of elements like nickel-56 forged in the explosion. The cow, however, had a light signature that was bizarrely smooth and featureless, lacking the specific chemical fingerprints we'd expect to see. It was also blazing hot, reaching temperatures of nearly 9,000 degrees Celsius, and it was releasing a tremendous amount of energy across the entire electromagnetic spectrum, from radio waves to gamma rays. This wasn't a slow, fading funeral pyre. It was more like a sudden, brilliant flashbulb popping in the cosmic dark. This bizarre combination of traits launched a fierce debate that continues to this day. One leading theory suggests the cow was a tidal disruption event, where a star wandered too close to a black hole and was violently ripped apart. But even that classic scenario doesn't perfectly fit the data. The event was too bright, too fast, and too hot. Another compelling idea is that we witnessed the exact moment a collapsing star gave birth to something new. This could be the formation of an incredibly active neutron star, a pulsar spinning at an immense speed and pumping energy into the surrounding debris. Or perhaps it was the birth of a black hole itself, one that immediately began to voraciously feed on the remains of the star that created it. The cow might be our first clear look at the inner engine of a stellar cataclysm, a cosmic maternity ward for some of the universe's most extreme objects. What makes the cow so profoundly important is that it shattered our existing categories. It forced us to admit that our textbooks were incomplete and that the universe has more than one way to blow a star to pieces. It became the prototype for a whole new class of objects we now call fast blue optical transients, or FBOT. Since its discovery, we've found a handful of other similar, strange, cow-like events, each helping us piece together a clearer picture. The cow was a reminder that for all our knowledge, the cosmos still holds profound surprises, acting as a direct message that when our instruments see something that doesn't make sense, it's usually a sign that we're on the verge of learning something entirely new. Just as the cow revealed the explosive secrets of stellar deaths, our next discovery shifted the cosmic searchlight from within galaxies to the vast, empty highways between them. The year was 2017, and for the very first time in human history, we were visited by an object from beyond our solar system. It was detected by the Pan-STARRS telescope in Hawaii, a silent, fast-moving speck against the backdrop of stars. In a beautiful nod to its nature as a scout from the distant unknown, it was given the name Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. This messenger was bizarre from the start. Its trajectory was hyperbolic, meaning it was moving far too fast to be bound by the sun's gravity. It had unquestionably come from interstellar space, a lone traveler on an epic journey that had likely lasted for millions of years before it briefly graced our neighborhood. But its path held the first major puzzle. As Oumuamua sped away from the sun, something strange happened. It wasn't just coasting, it was accelerating ever so slightly in a way that pure gravitational forces could not account for. This tiny, non-gravitational kick was the first clue that this object was not a simple, inert rock. Then there was its shape. Based on how its brightness changed dramatically as it tumbled through space, astronomers deduced that Oumuamua is incredibly elongated, like a cosmic cigar or a pancake. Its length was estimated to be up to 10 times greater than its width, a proportions unlike any asteroid or comet we've seen in our own solar system. This unusual form only deepened the mystery surrounding its origin and composition. The scientific community scrambled for a natural explanation for the acceleration. The most common cause for such behavior in comets is outgassing, when sunlight heats up icy surfaces, causing them to vaporize and jet out, acting like a tiny thruster. But here was the problem. Oumuamua displayed no visible coma, the fuzzy cloud of gas and dust that surrounds an active comet, and no detectable tail. If it was outgassing, it was doing so in a way we had never witnessed before, with dust perhaps too coarse to see or gases that our instruments couldn't easily pick up. Some scientists proposed it could be a shard of a Pluto-like world, rich in nitrogen ice that vaporized cleanly, or even a dust-free hydrogen iceberg, though that theory faced its own physical challenges. The absence of a conventional explanation is what opened the door, quite controversially, to a more speculative idea. Could Oumuamua be a piece of extraterrestrial technology? Astronomer Avi Loeb famously put forward the hypothesis that it might be a light sail, a thin, artificial object pushed by the radiation pressure from starlight, which would perfectly explain its unusual shape and its mysterious acceleration. While this remains a minority view within the scientific community, it sparked a necessary and profound debate about how we approach anomalies. Do we limit our hypotheses to what we already know, or do we dare to consider possibilities that, while unlikely, would fundamentally reshape our understanding of the universe? Regardless of its ultimate nature, Oumuamua's legacy is undeniable. It proved that interstellar objects are not just theoretical. They are constantly passing through our solar system, and we now have the technology to find them. This discovery launched entirely new branches of astronomy, with missions now being planned to intercept future visitors for a closer look. Oumuamua was a tiny, silent scout that delivered a monumental message: we are not isolated. The raw materials of other star systems, and perhaps even the evidence of other civilizations, might be sailing right past us, waiting for the moment we are clever enough to recognize them. If Oumuamua represented a mysterious solitary traveler, our next phenomenon is the complete opposite: a cosmic alarm clock that rings with such startling regularity it has revolutionized an entire field of astronomy. We're talking about fast radio bursts, or FRB. For years, these events were the ultimate cosmic flash in the pan, incredibly powerful bursts of radio waves that last just milliseconds, but in that blink of an eye release more energy than our sun does in decades. The frustrating part was their randomness. They'd appear out of nowhere from deep space, flash once, and then vanish forever, leaving astronomers with a single data point and a mountain of questions. Were these the final death cries of stars being vaporized by black holes, collisions between incredibly dense neutron stars, or perhaps signatures of something far more exotic, even artificial? All of that changed with one specific object, FRB 180916, discovered by the CHIME telescope in Canada. This wasn't just another burst. It was a repeater. Not only did it flash multiple times, but it did so on a schedule so precise it felt almost engineered. For roughly 4 days, it would fire off a burst or two every hour. Then it would fall completely silent for 12 days. After that, the cycle would start all over again, a perfect, predictable 16-day pattern. This was the first time anyone had ever seen such a clear, periodic cadence in a fast radio burst, and it immediately ruled out a whole class of theories. You see, a one-off explosion, like a star being torn apart or two objects colliding, can't happen twice. The fact that this FRB repeated on a loop meant its source had to survive its own outburst. It wasn't a destructive event, it was a recurring phenomenon, an object that was doing this over and over again. This crucial discovery shifted the entire conversation. The leading theory now points squarely towards extreme neutron stars, specifically a type called magnetars. Imagine a magnetar as a stellar corpse so dense that a teaspoon of its material would weigh billions of tons, and it has a magnetic field 1,000 trillion times stronger than Earth. These objects are cosmic powerhouses capable of unimaginable violence. The 16-day cycle is the real key to the mystery. Astronomers believe it acts as a cosmic lighthouse, but one with a very slow spin. The most plausible explanation is that the magnetar is in a binary orbit with another star. As it swings around its companion on its long, 16-day orbit, there are periods when the environment around it is calm enough for us to clearly see its burst. At other points in the orbit, it might be shrouded by a torrent of plasma blown off by its companion star, which effectively blocks its signals from our view. This perfect synchronization between the object's orbit and its bursting activity gives us a physical model we can actually test and study. The impact of this discovery cannot be overstated. It transformed FRBs from mere cosmic curiosities into usable tools for science. Because these waves travel across unimaginable distances, they pass through clouds of ionized gas and matter that we cannot otherwise see. By measuring how the burst signal is stretched and altered, astronomers can now map out this missing material, effectively weighing the invisible stuff between galaxies. FRB 180916, with its predictable location and behavior, provided the first reliable reference point for this new field of cosmology, turning these brilliant flashes into probes for understanding the vast, empty spaces that make up most of the universe. It proved that even the most mysterious cosmic signals, once decoded, can become some of our most powerful guides to the structure of everything. While the rhythmic pulses of FRBs gave us a new cosmic clock, other stars in the sky have captivated us by doing the exact opposite. They simply began to fade. Two of the most famous cases of stellar dimming involve stars that couldn't be more different. One, a nearby supergiant on the brink of death, and the other, a distant sun shrouded in a mystery that sparked the imagination of the entire planet. First, let's turn our gaze to the shoulder of the constellation Orion, to the brilliant red star Betelgeuse. For centuries, this star has been a dependable beacon, one of the brightest in our night sky. But in late 2019, astronomers and backyard stargazers alike watched in awe as Betelgeuse began to dim. And it didn't just dip slightly, it plummeted to about a third of its usual brightness, a change so dramatic it was visible to the naked eye. This wasn't a subtle flicker, it was a monumental event, given that Betelgeuse is a red supergiant, a massive star known to be in the final stages of its life. The immediate, thrilling question on everyone's mind was, is it about to go supernova? The idea was intoxicating. A supernova so close to us, a mere 650 light-years away, would be a historic event. It would become as bright as a full moon, visible during the day for weeks, and provide astronomers with an unprecedented front-row seat to the death of a star. The internet buzzed with excitement and speculation, but as telescopes around the world and in space trained their instruments on the Great Dimming, a more nuanced story began to emerge. The key data came from the Hubble Space Telescope and others, which revealed that the dimming wasn't symmetric. The star wasn't fading uniformly, which is what you might expect from an internal cataclysm. Instead, the data pointed to a colossal cosmic sneeze. Betelgeuse is a volatile, bubbling cauldron of a star, and it had ejected an enormous cloud of superheated plasma. This material traveled away from the star, cooled down, and condensed into vast quantities of dark, obscuring dust, which then passed between us and the star, blocking our view and creating the Great Dimming. By spring of 2020, the dust cloud had moved on, and Betelgeuse returned to its normal brilliance. The show was over and the star was safe for now. This event taught us invaluable lessons about the violent, messy processes that occur in these dying giants long before their final act. But several years before Betelgeuse grabbed headlines, a citizen science project called Planet Hunters unveiled a star with a dimming pattern so bizarre it made Betelgeuse look straightforward. This star, officially named KIC 8462852, but forever known as Tabby's star after its lead investigator, Tabby, was discovered by the Kepler Space Telescope. Kepler's job was to find planets by staring at stars and waiting for the tiny, periodic dip in light that occurs when a planet transits or passes in front of them. Tabby's star did dip, but its pattern was anything but periodic. It showed dozens of odd, aperiodic dimming events. Some were small, down by 1%, while others were absolutely massive, with one famous event blocking a staggering 22% of the star's light. To put that in perspective, even a Jupiter-sized planet would only block about 1% of a star's light. This was something on a scale we had never seen, and it defied all conventional explanation. The strangeness of the signal inevitably led to the most exciting, if unlikely, hypothesis. Could this be evidence of an alien megastructure? The idea, based on a concept known as a Dyson sphere, proposed that an advanced civilization might be building vast arrays of solar collectors around their star to harness its energy, and these arrays could be causing the irregular blocks of light. While scientists are always deeply skeptical of such extraordinary claims, the data was so unusual that they couldn't immediately rule it out. This propelled Tabby's star from an astronomical curiosity to a global phenomenon. A Kickstarter campaign raised over $100,000 for dedicated telescope time to study it further, and the world watched. What the continued observation revealed, however, was not the signature of intelligence, but once again the humble power of dust. Detailed spectroscopic analysis showed that the light being blocked was wavelength dependent. More blue light was being blocked than red light. This is a classic signature of dust particles which scatter blue light more effectively. A solid alien megastructure would block all wavelengths of light equally. The prevailing theory now suggests that Tabby's star is surrounded by a vast, chaotic cloud of dust and debris, likely from the breakup of a moon or a planet, or perhaps a family of comets on wildly eccentric orbits. The exact configuration remains a puzzle, but the material itself is almost certainly natural. Yet, the mystery is not entirely solved. We still don't know what could create such a complex and clumpy dust cloud, and why this particular star has it. The megastructure theory may have faded, but Tabby's star endures as a powerful symbol of how careful, methodical science investigates the extraordinary, and a reminder that sometimes the universe's natural explanations can be just as wondrous as any science fiction fantasy. While the mysteries of distant stars have captivated us, one of the most profound and unexpected discoveries in recent years was hiding right next door in the most unlikely of places. Venus has long been considered Earth's evil twin, a scorching, toxic hellscape with surface temperatures hot enough to melt lead and crushing atmospheric pressures 92 times greater than our own. Its clouds are made of sulfuric acid, and for decades the scientific consensus was clear. If there is one place in our solar system utterly incapable of hosting life, it is Venus. That ironclad assumption was spectacularly challenged in September 2020, when a team of astronomers made a bombshell announcement that sent shockwaves through the entire scientific community. Using two of the most powerful radio telescopes on Earth, the James Clerk Maxwell Telescope in Hawaii and the Atacama Large Millimeter Array in Chile, they had detected the spectral signature of a gas called phosphine in the temperate cloud decks of Venus. On its own, phosphine, a molecule made of one phosphorus and 3 hydrogen atoms, might not sound particularly exciting, but its presence on a rocky world is a massive red flag. Here on Earth, phosphine is exclusively associated with life. We find it in swamp mud where anaerobic bacteria thrive, and in the intestines of animals like penguins. While it can be created in minute quantities by extreme non-biological processes, like lightning in the clouds of Jupiter, those scenarios require immense pressures and temperatures not found on a rocky planet. Crucially, Venus's intense volcanic activity and surface chemistry should actively destroy phosphine molecules, not create them. Finding it there, and in such significant concentrations, was like smelling a freshly baked pie in a house that everyone believed had been abandoned for a century. It made absolutely no sense, and that is precisely what made it so electrifying. The researchers were extraordinarily cautious. They did not claim to have found life. Instead, they presented a tantalizing puzzle. They had detected a gas that, based on our current understanding of Venusian chemistry, should not exist. They had meticulously worked to rule out every known non-biological explanation, from unknown geological processes to micrometeorites delivering phosphorus, and nothing could account for the amount they were seeing. This left the door open, however slightly, to a truly breathtaking possibility. High in the Venusian atmosphere, about 50 to 60 kilometers above the surface, exists a relatively pleasant zone. The temperatures there are close to a comfortable 30 degrees Celsius, and the pressure is similar to that on Earth's surface. It is still a hostile environment, bathed in sulfuric acid droplets, but we know of extremophile microbes on Earth that can survive in similarly acidic conditions. Could floating, microbial life be the source of the phosphine? The idea of aerial biospheres, of life not on the ground but living its entire existence in the clouds, transformed Venus from a dead world into a potential haven for biology. As you would expect, the announcement was met with immediate and intense skepticism. This is how science at the frontier must work. Extraordinary claims require not just extraordinary evidence but relentless verification. Other teams of scientists rushed to reanalyze the data. Some argued that the signal itself was a misinterpretation, that the astronomers had mistakenly identified the spectral line of another, more common gas like sulfur dioxide. Others reprocessed the original data with different algorithms and claimed the phosphine signal vanished entirely. The original team stood by their work, refining their analysis and countering these criticisms, but the initial certainty began to fracture into a complex, ongoing debate. This back and forth wasn't a failure of science. It was science operating at its best, with competing groups rigorously testing a bold new idea to see if it could survive under the brightest possible spotlight. The profound importance of the Venus phosphine discovery lies not in a definitive answer, but in the powerful question it forced us to ask. It served as a monumental reminder that our understanding of planetary chemistry is still incomplete, and that the universe is always capable of surprising us. It sparked a renewed global interest in Earth's neglected twin, prompting space agencies to draw up plans for new missions specifically designed to probe its clouds, sample its atmosphere, and hunt for the true source of this mysterious gas. Whether the final verdict confirms a strange, unknown abiotic chemical process or, against all odds, points to biology, this discovery has already achieved something incredible. It has fundamentally changed the conversation, reminding us that the search for life in the universe might not require journeys to distant exoplanets, but could instead begin right in our own cosmic backyard, hidden in the acidic clouds of a world we thought we already knew. But if the mysteries of our solar system have taught us to question our assumptions, then the next discovery takes that lesson to a truly cosmic scale, challenging the very foundations of our understanding of the entire universe. We now arrive at what many cosmologists are openly calling a crisis, a looming crack in our model of reality known as the Hubble Tension. At its heart, this is a story about measuring the most fundamental property of our cosmos, its rate of expansion. For nearly a century, we've known the universe is growing larger, with galaxies rushing away from each other as space itself stretches. The number that describes how fast this is happening is called the Hubble constant, and pinning down its exact value has been one of the primary goals of modern astronomy. The crisis is this: we have two incredibly precise, incredibly reliable ways to measure this number, and they stubbornly refuse to agree. The first method looks into the deep past, back to the dawn of time itself. It uses the cosmic microwave background, the faint afterglow of the Big Bang that still permeates all of space. By mapping the tiny temperature fluctuations in this ancient light with exquisite detail, as done by the Planck satellite, we can work backwards using our best model of cosmic evolution, the lambda cold dark matter model, to predict what the expansion rate should be today. This is like recording the speed of a car the moment it left the factory and knowing the exact pressure of its tires and the power of its engine, calculating how fast it should be going now. This method gives us a very specific value. The second method measures the universe's current speed directly by looking at relatively nearby objects. Astronomers use what's called the cosmic distance ladder, a meticulous series of steps that builds out from well-understood stars in our own galaxy to more distant galaxies. They use pulsating stars called Cepheids and cataclysmic stellar explosions known as Type Ia supernova, which all have known intrinsic brightness. By measuring how much dimmer they appear to us, we can calculate their exact distance. Then, by measuring how much their light is stretched to redder wavelengths, the redshift, we can see exactly how fast they are moving away. This is like using a radar gun to directly measure the speed of that same car today. This method, refined over decades and confirmed by multiple independent teams, gives us a different, noticeably faster value for the Hubble constant. The problem is that these two answers, the one from the ancient universe and the one from the modern universe, don't match within their margins of error. The difference is about 5 or 6 kilometers per second per megaparsec. That might sound like a small, esoteric disagreement, but in the world of precision cosmology, it's a yawning chasm. It's the difference between the car's calculated speed and its radar gun speed being off by just enough to prove that our understanding of the engine, or the road, or the very laws of physics must be fundamentally wrong somewhere. This discrepancy is what we call the Hubble tension, and it has persisted and even grown more significant as our measurements have become more and more precise. It's a crisis because it suggests that our otherwise incredibly successful standard model of cosmology is incomplete. We might be missing a crucial ingredient. The most exciting possibility is that this points directly to new physics, forces or entities that we haven't yet discovered. Perhaps dark energy, the mysterious force accelerating the expansion, isn't constant as we've assumed. Maybe its strength has increased over the history of the universe, giving the expansion an extra kick that our model doesn't account for. Or perhaps there exists a previously unknown type of relativistic particle, often called dark radiation, that was zipping around in the early universe and altered the physics of the Big Bang's afterglow in a way we didn't anticipate. Other, more exotic ideas have been proposed, from the idea that dark matter possesses weird, unexpected properties to the notion that our universe is subtly inhomogeneous in a way that distorts our measurements. Some have even suggested, though it remains a last resort, that there might be a systematic error in one of the measurements that we are just too close to see. But after years of intense scrutiny, both camps, the early universe team and the local measurement team, have only become more confident in their results, double and triple checking their work. This means the error is likely not in our observations but in our theory. The Hubble tension is therefore not a failure of science but a brilliant beacon, a cosmic signpost pointing toward the next great revolution in our understanding. It's an invitation to look deeper and think bigger, assuring us that the universe still holds profound secrets about its own fundamental nature, waiting just beyond the edge of our current knowledge. Yet while the Hubble tension presents a cosmic-scale puzzle of physics and expansion, another recent discovery brings the search for meaning back to a profoundly human question: are we alone? For generations, the hunt for life beyond Earth has been a speculative dream, but now, thanks to the extraordinary power of the James Webb Space Telescope, it is rapidly becoming a tangible, data-driven science. And one world, known as K218b, has emerged as the most promising candidate we have ever found. Located 120 light-years away in the constellation Leo, this exoplanet isn't just another rocky blob or gas giant. It belongs to a completely new, hypothetical class of worlds that astronomers have dubbed Hycean planets, a portmanteau of hydrogen and ocean. Imagine a planet significantly larger than Earth but smaller than Neptune, with a massive, hydrogen-rich atmosphere enveloping a globe-spanning liquid water ocean. It's a world that is neither truly terrestrial nor fully gaseous, but something in between, potentially offering a vast and habitable environment unlike anything in our own solar system. The initial observations of K218b from other telescopes had already hinted at its intriguing nature, but it was the James Webb Space Telescope that truly peeled back the layers of its atmosphere. Using its incredibly sensitive instruments, Webb didn't just detect the atmosphere. It performed a detailed chemical census by watching the star's light filter through the planet's air as it transited. The results were staggering. Scientists confidently identified the presence of water vapor and carbon dioxide, two key ingredients in the recipe of life as we know it. But the most electrifying and controversial finding was the potential detection of something far more specific, a molecule called dimethyl sulfide, or DMS. Here on Earth, dimethyl sulfide is extraordinarily significant. It is not produced by any known geological or chemical process. Its sole source is biological, specifically phytoplankton in marine environments. The smell of the sea, that distinct, pungent, briny odor you get at the beach, that's largely dimethyl sulfide. Finding a hint of this gas in the atmosphere of a Hycean world is quite literally like catching a distant whiff of an oceanic breeze from 120 light-years away. It is the kind of signature that, if confirmed, would represent the most compelling evidence for life beyond Earth in human history. But, and this is the most critical part, the team at the University of Cambridge who made the discovery have been exceptionally clear and cautious. They are not claiming to have found proof of life. They are reporting a data point with a low statistical significance, a hint that requires an immense amount of further verification. The signal for DMS is faint, and it overlaps with other potential methane-related signals, making it incredibly difficult to disentangle with absolute certainty. This is the very frontier of science, where a breathtaking possibility hangs on the edge of what our current technology can resolve. The next step is more observation time with Webb, aiming to gather more data points to see if this tantalizing signal grows stronger and clearer, or if it fades into the background noise. The profound importance of K2-18b lies not just in a single gas, but in the paradigm shift it represents. For decades, the search for life has focused on finding a second Earth, a rocky planet of a similar size orbiting in a sun-like star's habitable zone. K2-18b shatters that narrow view. It orbits a cool red dwarf star, and its year is just 33 days long. It is likely tidally locked, with one side in perpetual daylight and the other in endless night. And it is a mini-Neptune, a type of planet we don't even have in our own solar system. The revelation that such a world could not only possess an atmosphere but also showcase the chemical markers that might suggest habitability, or even inhabited, dramatically expands the cosmic real estate we consider promising. It forces us to abandon our Earth-centric biases and consider that life, if it exists out there, might be thriving in environments we once thought were utterly hostile. A confirmed detection of dimethyl sulfide on K2-18b would irrevocably change everything. It would mean that the processes that led to life on our pale blue dot are not a unique miracle but a common cosmic occurrence. It would suggest that the universe is not only teeming with planets but potentially teeming with living planets. The journey to confirm this hint will be long and painstaking, requiring repeated observations and perhaps even future, more powerful telescopes. But for now, K2-18b stands as a beacon of possibility, a testament to how far our technology has come, and a humbling reminder that the answer to humanity's oldest question may be hiding in the atmosphere of a distant water world, waiting for us to learn how to read the signs. But if the discovery of a single promising world like K2-18b ignites our imagination about biology, the next phenomenon forces us to contemplate the truly staggering architecture of the cosmos itself, on a scale so vast it defies human comprehension. We now journey to the southern sky, to a discovery that reminds us our own galaxy was, until very recently, hiding a secret in plain sight, or rather, hiding it from sight entirely. This is the story of the South Pole Wall, a gargantuan cosmic structure that ranks as one of the largest ever observed, a filament of galaxies so immense it stretches over 1.4 billion light-years from end to end. To grasp that scale, consider that our entire local group of galaxies, including Andromeda and the Milky Way, is only about 10 million light-years across. This wall is 140 times larger than our entire local neighborhood. For decades, this colossus remained hidden from us due to a simple but frustrating cosmic coincidence. Its location is directly behind the plane of our own Milky Way galaxy. This region of the sky is known to astronomers as the zone of avoidance. From our perspective on Earth, the dense band of the Milky Way is packed with stars, gas, and dust that create a brilliant, glowing veil. This veil is beautiful to look at, but it acts like a cosmic curtain, completely obscuring our view of the universe beyond it. It's as if we've been trying to map the world while standing in a dense, luminous fog that blocks our view of an entire continent. Traditional optical telescopes were utterly useless for peering through this zone. The light from distant galaxies is absorbed and scattered by all the intervening material. The breakthrough came not from seeing the light, but from mapping the motion. An international team of researchers used a clever technique to pull back the curtain. Instead of relying on light, they turned to redshift surveys, which measure how fast galaxies are moving away from us due to the expansion of the universe. By meticulously cataloging the subtle velocities of thousands of galaxies near the zone of avoidance, they could infer their positions in three-dimensional space. It's a cosmic version of sonar, using motion to paint a picture of structure. This data was then combined with sophisticated gravitational models to predict the influence of unseen mass. The resulting map revealed the unmistakable outline of the South Pole Wall, a vast sheet-like superstructure of galaxies, galaxy clusters, and unimaginable amounts of dark matter, all woven together by gravity into a single, coherent filament that forms a border to a cosmic void. The existence of such a massive structure, especially one that is relatively close to us in cosmic terms, presents a serious challenge to our best models of how the universe evolved. The prevailing lambda-cold dark matter model, which has been incredibly successful at explaining the large-scale distribution of galaxies, includes a principle known as the cosmological principle. This principle states that on the very largest scales, the universe should appear roughly uniform and isotropic. It should look the same in all directions without any preferred center or overwhelming dominant structures. While the model predicts the formation of filaments and walls as part of the cosmic web, finding one as enormous as the South Pole Wall and one that seems to be connected to other nearby superstructures pushes the upper limits of what we thought was possible. It hints that the universe might be clumpier on larger scales than our simulations have predicted, suggesting that the subtle tug of dark matter and the force of gravity may have been even more efficient at gathering matter together than we ever imagined. The South Pole Wall is more than just a new entry in a catalogue of big things. It is a profound reminder of the limits of our own perspective. For all our powerful technology, we are still inhabitants of a single galaxy, and our own celestial backyard can still obscure wonders of unimaginable scale. Its discovery proves that by combining ingenuity with new observational techniques, we can begin to map the entirety of our cosmic environment, even the parts we cannot directly see. It stands as a testament to the fact that the greatest structures in the universe might still be lurking, unseen, waiting for us to develop the tools and the cleverness to find them. While the South Pole Wall revealed a structure of almost unimaginable scale, our next discovery draws our attention to a cosmic object at the opposite end of the spectrum, one so small and elusive that it earned a name of myth and magic, the unicorn. This isn't a creature from a fairy tale, but a black hole, and its discovery in the constellation Monoceros, which translates to the unicorn, is a brilliant testament to the ingenuity of astronomers who are learning to find the invisible by watching the dance of the visible. For decades, the hunt for stellar mass black holes has relied on their most dramatic feature, their appetite. We often find them in X-ray binary systems, where a black hole is actively pulling material away from a companion star. As this superheated gas spirals into the accretion disk, it emits powerful X-rays, creating a beacon we can detect across the galaxy. But this method has a massive blind spot. What about all the black holes that are not actively feeding? What about the dormant ones, the cosmic ghosts simply drifting through space alongside a companion, exerting their gravity but not consuming anything? Theories suggested there should be a vast population of these quiet black holes, but without their telltale X-ray shine, they were nearly impossible to find. The unicorn offered a new solution. Astronomers at Ohio State University were studying a common red giant star, one known simply as V723 Monocerotis. At first glance, it seemed utterly ordinary, but something about its motion was subtly off. The star's light exhibited a strange but consistent pattern of shifting, as if it were being tugged back and forth by an unseen companion. This is the classic signature of a binary system, but the companion itself was completely dark, emitting no light whatsoever. By meticulously analyzing the tug-of-war between the visible star and its invisible partner, the team could calculate the mass of the hidden object. The result was astonishingly small, just about 3 times the mass of our Sun. This tiny mass is the key to the mystery. It places the object squarely in what astrophysicists call the mass gap. For years, we had observed 2 distinct families of cosmic corpses: neutron stars, which are the incredibly dense remnants of dead stars and typically top out at around 2.2 solar masses, and black holes, which we had only found with masses starting at around 5 times that of the Sun. This left a puzzling gap between 2 and 5 solar masses. What happens in that gap? Do stars not collapse into objects within that range, or have we simply been unable to find them? The unicorn, with its estimated 3 solar masses, sits perfectly within this gap, making it a Rosetta Stone for understanding stellar evolution. Its discovery was a masterclass in indirect detection. Instead of looking for X-rays, the team looked for the gravitational fingerprint of the black hole on its companion. The red giant is tidally distorted, stretched slightly into a teardrop shape by the black hole's immense pull. This effect, along with the precise orbital period of the system, provided all the evidence needed to confirm the invisible object's presence and mass. It's a technique that opens an entirely new window onto the cosmos. We are no longer limited to finding black holes that are screaming with energy. We can now find the silent ones, the ones that whisper their presence through gravity alone. The implications are staggering. If the unicorn is the first of its kind to be found with this method, it suggests that the galaxy could be filled with thousands, even millions, of these quiet, low-mass black holes. They have been hiding in plain sight all along, their presence betrayed only by the gentle wobble of the stars they orbit. Finding more of these objects will finally allow us to map the lower end of the black hole mass spectrum, solve the mystery of the mass gap, and give us a complete picture of how stars live, die, and transform into the universe's most enigmatic objects. The unicorn is far more than a curiosity. It is a pioneer, proving that even the darkest, smallest, and most hidden entities in the cosmos cannot escape our notice when we learn how to read the subtle language of gravity. Just as the unicorn showed us how to find the invisible through subtle gravitational tugs, our next discovery proves that sometimes the universe presents us with a mystery so blatant and bizarre that we can't believe we missed it for so long. These are the odd radio circles, or ORC, and their name doesn't even begin to cover just how strange they truly are. The story begins with a new era of radio astronomy, specifically with the Australian Square Kilometre Array Pathfinder, or ASCAP, a powerful telescope designed to map the sky in radio waves with unprecedented speed and detail. It was during one of these vast surveys that astronomers spotted something they had never seen before: faint, perfect circles of radio emission just hanging in space. They weren't centered on any visible galaxy or star. They were simply there, ghostly cosmic rings. The initial assumption was that these were likely familiar objects, perhaps the radio remnants of supernova explosions. But that idea was dismissed almost immediately. These ORCs were far too large, often hundreds of thousands of light years across, several times the diameter of our entire Milky Way galaxy. A supernova remnant might be a few dozen light years wide at most. They were also perfectly symmetrical and isolated, with no visible object at their center to explain their existence. Even more perplexing, when astronomers pointed other telescopes, like optical or infrared observatories, at the exact same spots in the sky, they saw absolutely nothing. The ORCs were completely invisible except in the radio part of the spectrum. It was as if the universe had drawn giant, ethereal circles on a canvas only one type of instrument could see. The hunt for an explanation quickly turned into a race to develop plausible theories, each one more fantastic than the last. One of the leading ideas proposes that an ORC is the aftermath of a truly cataclysmic event, a starburst termination shock. This theory suggests that in the distant past, a galaxy underwent a ferocious period of star formation, creating millions of new stars in a relatively short time. These massive new stars would have lived fast and died young, exploding as supernovae in rapid succession. The combined force of all these explosions could have blasted a spherical shockwave of material outwards at incredible speeds, plowing into the thin gas that exists between galaxies. This immense, expanding shell of energetic particles would then generate radio waves, creating the perfect circle we observe. In this scenario, the central galaxy has since calmed down and faded from view, leaving only this gigantic, fading radio bubble as a testament to its violent, youthful outburst. Other theories venture into even more exotic territory. Could these circles be the literal throats of wormholes? The idea is that a wormhole, a theoretical tunnel through space-time, might be surrounded by a sphere of high-energy particles. If we were to look down the tunnel, we might see it as a circular ring. Another compelling thought links ORCs to the jets from supermassive black holes. Sometimes these black holes erupt, shooting twin jets of plasma in opposite directions. If one of these jets were firing directly at Earth, we might not see the long, thin jet itself, but instead see a circular head on view of its energetic lobe, like looking directly into the nozzle of a hose. Yet, even this doesn't perfectly fit all the data, as the circles seem too perfectly formed and isolated. The true power of the ORC discovery lies not in any single solution, but in what it represents. It is a stunning example of a pure, unexpected anomaly. There was no theory predicting these objects. They were found simply because we built a new telescope with a new capability and looked at the sky in a way we never had before. They remind us that our maps of the universe are still filled with blank spaces labeled "Here be dragons," and that every time we create a new lens through which to view the cosmos, we should fully expect to see dragons, or in this case, inexplicable giant rings staring back at us. The study of ORCs is still in its infancy, but it already guarantees that our universe holds forms and phenomena beyond our current imagination, waiting for our curiosity and technology to finally reveal them. But if the odd radio circles are unexpected structures of energy, our next destination is defined by a profound and unsettling absence. We now venture into one of the greatest nothings ever discovered, a region of space so empty it has earned the ominous nickname the Great Nothing. This is the Boötes Void, and to stand at its imaginary center would be to experience a loneliness beyond human comprehension. Located about 700 million light-years from Earth in the constellation of Boötes the Herdsman, this void is not a simple gap between galaxy clusters. It is a near-perfect spherical region of space stretching an almost unimaginable 330 million light-years across. To grasp that scale, consider that our entire local group of galaxies could fit inside it over 7,000 times. If you were to place the Milky Way at one edge of the void, the light from our galaxy would take 330 million years to travel in a straight line before it finally hit another galaxy on the far side. This is a volume of space that contains almost nothing. The existence of such a colossal void directly challenges our understanding of how the universe is structured. The prevailing lambda cold dark matter model does predict that the cosmos should resemble a vast cosmic web, with dense filaments of galaxies surrounding great, empty bubbles known as voids. But the Boötes void is different. It is orders of magnitude larger than what our best simulations predict should be possible. Based on our models, a void of this size should contain roughly 2,000 galaxies. Instead, astronomers have only been able to confirm the presence of about 60. That's not just empty, that's a vacuum of matter on a scale that seems to defy the laws of probability and the very notion of a roughly uniform universe. Theories for its existence range from the soberly scientific to the wildly speculative. The most straightforward explanation is that it is simply a statistical fluke, a 1 in a billion coincidence where several smaller voids have merged together over billions of years to form one supervoid. In an infinite universe, the argument goes, even the most improbable structures must appear somewhere. But the sheer scale of the Boötes void makes many cosmologists uncomfortable with this answer, as it pushes the limits of what we consider a plausible fluctuation in the density of the cosmos. Another compelling theory delves into the nature of dark energy, the mysterious force accelerating the expansion of the universe. Perhaps in regions like the Boötes void, where the gravitational pull of matter is exceptionally weak, dark energy operates with greater efficiency, causing space within the void to stretch faster than the space in the surrounding, denser regions. This would effectively inflate the void from the inside, pushing any remaining galaxies out towards the edges and making the emptiness even more profound over time. It would be a runaway process where emptiness begets more emptiness. Then there is the most provocative and fringe hypothesis, one that captures the imagination but resides firmly in the realm of science fiction. Could the Great Nothing be evidence of a type Roman III civilization on the Kardashev scale? This theoretical civilization would have mastered the art of harnessing the energy of not just a star, but an entire galaxy or even a cluster of galaxies. The idea suggests that such an unfathomably advanced species might eventually engage in a process called stellar harvesting, methodically dismantling stars and galaxies over eons to fuel their cosmic scale projects, leaving behind a vast, empty region of space as the ultimate signature of their existence. While there is precisely zero empirical evidence to support this idea, and most scientists dismiss it as an entertaining but unsupported thought experiment, it serves a valuable purpose. It forces us to confront the sheer strangeness of the void and question what other natural or unnatural processes could possibly account for such a staggering absence. The true scientific importance of the Boötes void is not in proving wild theories about aliens, but in what it teaches us about the limits of our own models. It is a colossal anomaly that our current understanding of cosmology struggles to explain. It stands as a stark, dark reminder that the universe is under no obligation to conform to our expectations, and that the largest structures and the largest absences might still hold the keys to unlocking the next great revolution in our understanding of dark matter, dark energy, and the ultimate fate of the cosmos. Yet after exploring the vast emptiness of the Boötes void, our journey brings us to one of the most tangible and iconic triumphs in modern astronomy, a moment that transformed a theoretical phantom into a visible reality. On April 10, 2019, the world was presented with an image that had, until that very day, existed only in the realm of equations and imagination, the first direct visual evidence of a black hole. This was the supermassive giant known as M87 star, residing at the heart of a galaxy 55 million light-years away, and its portrait was nothing short of revolutionary. The image itself was hauntingly beautiful, a fiery ring of orange and yellow light encircling a perfect circle of profound darkness. This was the black hole's shadow, its event horizon, the point of no return where gravity becomes so overpowering that not even light can escape. For the first time in human history, we were staring directly into the abyss. Capturing this image was a feat of such monumental difficulty that it required a telescope literally the size of the entire planet. This was the work of the Event Horizon Telescope collaboration, which is not a single instrument but a network of 8 radio observatories strategically positioned across the globe, from the high deserts of Arizona and the peaks of Hawaii to the frigid landscapes of the South Pole. By synchronizing these telescopes with atomic clocks and having them all observe M87 star simultaneously, astronomers effectively created a virtual dish as wide as Earth itself. This technique, known as very long baseline interferometry, provided the angular resolution necessary to resolve an object that, from our vantage point, appears as small as a donut on the surface of the Moon. The amount of raw data collected was staggering, so immense it couldn't be transmitted over the internet. Instead, hundreds of hard drives filled with data were physically flown from each observatory to central processing centers in the United States and Germany, where supercomputers spent years correlating and assembling the information into a single historic picture. The final image was a spectacular validation of Einstein's general theory of relativity, which predicted over a century ago that a black hole's immense gravity would warp the very fabric of spacetime, bending light around it to form a bright ring. The dark shadow at the center isn't the black hole itself, but a region where light rays that would have reached us are instead captured by the event horizon. The size and shape of this shadow match the predictions of relativity with uncanny precision, proving that Einstein's equations hold true even in the most extreme gravitational environment in the universe. Any significant deviation from the predicted shape could have hinted at flaws in our understanding of gravity, potentially pointing the way to new physics. Instead, the image revealed a near-perfect circle, a stunning testament to the enduring power of a theory conceived on paper long before we had the technology to test it in such a dramatic way. Beyond confirming what we already knew, the image of M87 star opened entirely new doors for scientific inquiry. The bright, lopsided ring of light provided crucial information about the black hole's spin and the direction of its rotation, while also offering a direct view of the chaotic accretion disk of superheated gas and plasma swirling around it at near light speed. This data is helping scientists understand the physics of how black holes consume matter and how they launch their incredible jets of plasma, like the one erupting from M87 that stretches thousands of light years into space. The achievement stands as a powerful symbol of what humanity can accomplish through global collaboration, patience, and sheer intellectual curiosity, transforming a cosmic mystery into a familiar sight and forever changing our relationship with the most enigmatic objects in the cosmos. But just as the Event Horizon Telescope gave us an unprecedented look at the aftermath of cosmic violence on a supermassive scale, another discovery has revealed the beautiful and delicate aftermath of a stellar collision much closer to home. This brings us to a truly singular object, a celestial jewel box known as the Blue Ring Nebula. Discovered in 2004 by NASA, a galaxy evolution explorer, a space telescope designed to observe the universe in ultraviolet light, this object stood out for one simple reason: it was the only one of its kind ever found. For 16 years, it remained a profound mystery, a perfect, symmetrical ring of vibrant blue light encircling a central star with no clear explanation for its existence. The blue in its name is a bit of a cosmic trick of the eye. The ring itself doesn't actually glow blue. The color is a false color representation used by astronomers to visualize the intense ultraviolet light that the structure emits, which is invisible to our eyes. The central star, known as TYC 2597257761, appeared to be a fairly ordinary, though slightly aging, star. The puzzle was the ring itself. What could possibly create such a vast, expanding shell of ultraviolet fluorescence? The leading theory for years invoked a disk of dust around the star, but that never quite fit all the observational data. It wasn't until a team of scientists employed a full decade and a half of data from multiple ground and space-based observatories that the true, spectacular story began to emerge. They weren't looking at a simple disk or a standard planetary nebula. They were witnessing the fresh, glowing aftermath of a stellar merger, a cosmic car crash of epic proportions that occurred just a few thousand years ago, a mere blink in astronomical time. The current theory is both violent and elegant. The story begins with two stars, a binary pair locked in a gravitational dance. One was likely similar to our own Sun, while the other was a smaller, lower-mass star. Over billions of years, as the larger star began to exhaust its fuel and swell into a red giant, their dance turned deadly. the smaller star was drawn inexorably inward, spiraling toward its companion until it was completely engulfed. In a final, violent act of consumption, the larger star tore its smaller partner apart. But this wasn't a clean process. The energy of this merger blasted much of the material from both stars out into space at tremendous speeds, not as a messy cloud, but as two conical jets shooting out in opposite directions from the central wreckage. From our vantage point here on Earth, we are looking directly down the barrel of one of these cones, which creates the illusion of a perfect circular ring surrounding the system. The brilliant blue ultraviolet glow is the final piece of the puzzle. This expanding shell of debris is racing outward at breakneck speed, and as it slams into the clouds of gas and dust that already existed in the interstellar medium, it creates a colossal shockwave. This shock front heats the material to incredible temperatures, causing it to glow with the intense ultraviolet light that makes the nebula visible to our telescopes. What we are seeing is the cooling embers of a stellar catastrophe, the brief, luminous echo of two stars becoming one. This phase is incredibly short-lived. Within a few thousand more years, the shockwave will have dissipated and the glow will have faded, leaving behind a single, rejuvenated star and a secret history that would have been completely invisible to us if we hadn't looked at just the right moment. The Blue Ring Nebula is therefore a priceless time capsule. It captures a fleeting stage of stellar evolution that has been theorized for decades but almost never observed directly. It provides a living laboratory to study the immediate consequences of a stellar merger, helping us understand how such events can reshape solar systems, forge new chemical elements, and even create the conditions for new planets to form from the ashes of the old ones. It serves as a powerful reminder that the night sky, for all its apparent permanence, is a dynamic and ever-changing arena where the most dramatic events unfold on timescales beyond human comprehension, leaving behind only beautiful, enigmatic clues for us to decipher. While the image of M87 star and the glowing aftermath of the Blue Ring Nebula represent monumental achievements in modern astronomy, some of the most captivating cosmic mysteries are not found in stunning visuals but in a single, tantalizing line of data from a bygone era. This brings us to an enigma that has baffled scientists and fueled the imagination of the public for over 4 decades, the WOW signal. It was the evening of August 15, 1977, at the Big Ear Radio Telescope in Delaware, Ohio. This massive instrument, operated by Ohio State University, was part of the groundbreaking Search for Extraterrestrial Intelligence, or SETI, program, methodically scanning the sky for any narrowband radio signal that could indicate an artificial source. That night, as the telescope slowly swept across the rich starfields of the constellation Sagittarius, something extraordinary happened. A powerful, unwavering burst of radio noise flooded the receiver. It was so intense and so perfectly matched to the expected signature of an interstellar beacon that the computer printout recording the data prompted volunteer Jerry Amon to simply circle the alphanumeric sequence and scrawl, "WOW," in the margin, giving the signal its immortal name. The data itself was both incredibly promising and deeply frustrating. The signal was a narrowband transmission at exactly 1,420 MHz, a frequency that is scientifically significant because it's one of the main emission lines of neutral hydrogen, the most common element in the universe. Many scientists had previously suggested that this would be a natural, watering hole frequency for civilizations trying to announce their presence. The signal lasted for the full 72-second window that the Big Ear telescope could focus on any single point in the sky, and then it vanished, never to be detected again despite dozens of dedicated follow-up searches over the years. It had all the hallmarks of a deliberate broadcast. It was strong, isolated, and appeared to originate from a specific, unremarkable point in space devoid of any obvious stars or planets. For decades, the WOW signal has stood as the best candidate humanity has ever received for a potential alien communication. the closest we've come to feeling that we are not alone in the cosmos. It has been the subject of countless documentaries, books, and scientific papers, a symbol of both the promise and the profound challenge of SETI. The central mystery has always been its one-off nature. If it was a deliberate broadcast from a distant civilization, why was it never repeated? Was it a targeted message that simply missed its mark? A catastrophic event that silenced the sender immediately after transmission? Or was it something else entirely, a natural phenomenon so rare we have yet to witness it again? In recent years, a new and highly specific theory has emerged, one that seeks to demystify the signal by tying it to a far more mundane, yet still fascinating celestial object. In 2016, astronomer Antonio Paris proposed that the signal might not have come from the depths of interstellar space, but from much closer to home. His research pointed to the passage of a comet, specifically two comets known as 266P/Christensen and 335P/Gibbs, were calculated to have been transiting through the exact patch of sky in Sagittarius that the Big Ear telescope was monitoring on that August night. Comets are surrounded by massive clouds of hydrogen gas, released as solar radiation vaporizes their icy nuclei. As this cloud expands, it can emit a strong, narrowband radio signal at that magic frequency of 1420 MHz. The theory suggests that as one of these comets drifted through the telescope's field of view, its hydrogen cloud generated the powerful, transient burst that was recorded. This comet theory, however, has faced significant skepticism and rigorous challenges from the scientific community. Critics were quick to point out a major flaw. The Big Ear telescope used two separate feed horns that observed the sky slightly apart from each other. A signal from a genuine point source in space would have been detected by one horn and then, as the Earth's rotation moved the telescope, by the second horn a few minutes later. The WOW signal was only ever picked up by one of the two horns, which is inconsistent with how a comet, a slowly moving object, would have been observed. Furthermore, subsequent attempts to detect similar signals from other known comets have largely failed to produce anything nearly as powerful or clean as the original WOW signal. While the comet theory offers a plausible natural explanation, it has not been widely accepted as the definitive solution, leaving the door to the mystery still very much open. The true legacy of the WOW signal, therefore, may not be in its solution, but in the profound questions it continues to raise about our place in the universe and our methods of exploration. It remains the ultimate cold case, a data point that is both incredibly compelling and utterly insufficient. It is a reminder of the immense difficulty of SETI, an endeavor that is often described as listening for a whisper in a hurricane. The vastness of space, the countless frequencies to monitor, and the fleeting nature of any potential signal mean that patience and persistence are our greatest assets. The WOW signal, whether it was a passing comet or something far more extraordinary, serves as a perpetual beacon of curiosity. It validates the search itself, proving that the cosmos is capable of producing phenomena that stop us in our tracks and force us to wonder, to debate, and to keep looking up, listening for the next whisper that might one day change everything. But while the WOW signal represents a fleeting whisper from the cosmos, our next discovery pulls our focus to the grandest, most pervasive force shaping the entire universe, an architecture so vast it connects everything we see and a great deal that we cannot. We are talking about the cosmic web, the fundamental skeleton of the cosmos, and the mysterious energy that seems to be stretching it apart. For centuries, astronomers charted the heavens by mapping stars and galaxies as individual points of light. But as our technology advanced, a deeper pattern began to emerge. We discovered that galaxies are not scattered randomly through the void like lonely islands. Instead, they are gathered into immense clusters, which themselves are linked by long, delicate threads of dark matter and gas, forming a web-like structure of breathtaking scale and beauty. This is the cosmic web, the largest pattern in nature, and mapping it has been one of the greatest scientific endeavors of our time. The true substance of this web is not the bright galaxies we see, but the invisible scaffolding of dark matter. This mysterious substance, which does not emit, absorb, or reflect light, makes up about 85% of all the matter in the universe. We cannot see it directly, but we can map its presence through its immense gravitational pull. Imagine space as a vast, invisible landscape of hills and valleys created by the mass of dark matter. Ordinary matter, the gas, dust, and stars that form galaxies, simply flows downhill into these gravitational valleys. Where the dark matter is densest, it pulls in enough gas to ignite stars and birth galaxies, creating the brilliant nodes and clusters we observe. The filaments themselves are the ridges connecting these valleys, rivers of dark matter along which gas and entire galaxies slowly drift. For a long time, this web was a theoretical prediction, but recent surveys like the Sloan Digital Sky Survey have now made it visible, using the precise positions of millions of galaxies to trace out the faint gossamer threads stretching across billions of light-years, confirming that the universe is indeed structured like a spider's web on a colossal scale. However, the story doesn't end with mere mapping. As we began to track the precise movements of galaxies within this web, astronomers noticed something deeply strange, a behavior that defied the simple pull of gravity. We expect galaxies to be drawn towards the densest knots of the web, the massive clusters, and they are, but on the very largest scales, something else is happening. The expansion of the universe is not just continuing, it is accelerating. Galaxies are being pushed apart from one another at a faster and faster rate. This observation was so shocking that it earned the Nobel Prize in Physics in 2011. The cause of this acceleration is what we call dark energy, a repulsive force that seems to be an inherent property of space itself. It acts in direct opposition to gravity, and as the universe grows larger and emptier, dark energy's push becomes the dominant force, winning the cosmic tug-of-war. The true breakthrough in understanding the interplay between the cosmic web and dark energy came from studying the peculiar velocities of galaxies, how they move relative to the overall expansion of the universe. While gravity pulls galaxies along the web's filaments toward clusters, detailed measurements suggest that on scales beyond a few 100 million light-years, the flow of galaxies begins to be influenced by this repulsive push. It's as if the cosmic web, this beautiful, gravity-built structure, is itself being stretched and diluted by a force working from within the empty spaces between the threads. The voids, like the Boötes void we discussed earlier, aren't just empty. They are the engines of acceleration, where dark energy's repulsive effect is strongest because the gravitational pull of matter is weakest. This creates a fascinating large-scale dynamic. While gravity builds the web locally, dark energy governs its ultimate fate globally, determining how this vast cosmic architecture will evolve over trillions of years. This discovery forces us to confront one of the most profound mysteries in all of science. What exactly is dark energy? The leading hypothesis is that it is the cosmological constant, an energy density inherent to the vacuum of space itself, as first proposed by Einstein. If this is true, its strength should remain constant over time, but other theories suggest it could be a dynamic force field that has changed throughout cosmic history. Some even more radical ideas propose that our understanding of gravity itself is flawed on the largest scales, and that Einstein's theory of general relativity needs to be modified. Each of these possibilities carries staggering implications for the fate of the cosmos. A constant dark energy points toward a future where the universe expands forever into a cold, dark, and empty eternity, every galaxy isolated beyond the observable horizon of every other. A dynamic dark energy could lead to even more dramatic fates, like a big rip where the fabric of spacetime itself is torn apart. The ongoing study of the cosmic web is therefore much more than cartography. it is a direct investigation into the laws of physics and the ultimate destiny of everything. By meticulously measuring how galaxies move within this web, how the filaments evolve, and how the voids expand, we are essentially taking the pulse of the universe. Each new galaxy survey, each more detailed map, brings us closer to understanding the true nature of dark energy. This invisible framework, once just a theorist's dream, has become our most powerful tool for probing the deepest secrets of existence, revealing a universe built by gravity but driven by a mysterious, repulsive force that we are only just beginning to comprehend. Yet for all the grandeur of the cosmic web and the invisible push of dark energy, one of the most profound breakthroughs in modern astronomy came from tracking a particle so tiny and elusive it was once thought impossible to trace. This is the story of the ghost particle, the neutrino, and the day we finally caught one with a cosmic return address. Neutrinos are among the most abundant particles in the universe, but they are also the most antisocial. Trillions of them are passing through your body every second, coming from the sun, from nuclear reactions in the Earth, and from the depths of space. They are called ghost particles because they have almost no mass and no electric charge, which means they rarely interact with anything. They can fly straight through a light year of solid lead without so much as a bump. This makes them incredibly difficult to detect, but it also makes them incredibly valuable messengers, because they are not deflected by magnetic fields or absorbed by dust and gas. They travel in perfectly straight lines from their source, carrying pristine information about the most violent events in the cosmos. The challenge has always been catching one with enough energy to point back to its origin, and then being lucky enough to have other telescopes see something at that exact spot in the sky. That moment of incredible luck and preparation arrived on September 22, 2017. Deep inside the ice at the South Pole, the Ice Cube Neutrino Observatory, a gigantic detector built into a cubic kilometer of pristine Antarctic ice, recorded a single momentous event. A neutrino possessing an astonishing energy of about 290 tera-electronvolts, that's over 40 times the energy of protons in the Large Hadron Collider, had slammed into an atomic nucleus in the ice. This rare collision created a secondary particle that emitted a faint flash of blue light, which IceCube's thousands of embedded optical sensors detected. Critically, because this array is buried so deep, it could trace the angle of the neutrino's path back to a specific point of origin in the sky. Within seconds, an automated alert was sent out to observatories around the world, a cosmic wake-up call pointing to a patch of sky near the constellation Orion. Telescopes of every kind immediately swiveled to look, and there, right where the neutrino pointed, was a dazzling source of high-energy gamma rays. It was a blazar, an active galactic nucleus known as TXS 0506 plus 056, located about 4 billion light-years away. A blazar is one of the most energetic objects in the universe, a galaxy with a supermassive black hole at its core that is actively feeding on surrounding material. As matter spirals in, some of it gets funneled into powerful jets of radiation and particles that shoot out from the poles at nearly the speed of light. We just happen to be looking directly down the barrel of one of these jets. This particular blazar was in a period of extreme outburst, flaring brilliantly in gamma rays, and it was now clear that it was also a powerful particle accelerator, shooting out these incredibly high-energy neutrinos. This single detection was a landmark event for one simple reason. It was the first time we had ever definitively identified the source of a high-energy cosmic neutrino. But the story gets even richer. When the IceCube team went back through years of archival data, they found evidence of a previous cascade of lower-energy neutrinos from the same blazar back in 2014 and 2015. A flare that had gone unnoticed at the time because we weren't yet looking for these correlations. This confirmed that TXS 0506 plus 056 wasn't just a one-time offender, it was a steady factory for these ghost particles. The implications of this discovery are monumental, marking the dawn of a truly new era called multi-messenger astronomy. For centuries, we have studied the universe almost exclusively through light, from visible waves to radio and gamma rays. But light can be obscured, distorted, and scattered. Now, we have proven we can effectively study the cosmos using multiple messengers simultaneously: light, gravitational waves, and now neutrinos. Each one tells us a different part of the story. The gamma rays from the blazar's jet told us about the incredible electromagnetic energy being released, while the neutrino told us something even more crucial: that protons or other charged particles were being accelerated to immense speeds within those jets. This finally solves a century-old mystery about the origin of cosmic rays, the high-energy protons that constantly bombard our atmosphere. We've never been able to trace them back to their source because their paths are scrambled by magnetic fields on their long journey through space. But neutrinos are the smoking gun. They are created in the same particle acceleration processes that produce cosmic rays, and because they travel in straight lines, they point directly back to the cosmic ray factory. By catching this one ghost particle, we didn't just find a source, we unlocked an entirely new way to see the universe, using the most elusive particles in existence as our guides to the most powerful engines in the cosmos. Yet as we use ghost particles to map the most energetic engines in the distant universe, another discovery is unfolding much closer to home, in the frozen, dark reaches of our own solar system. A discovery that suggests a massive secret is still hiding in our cosmic backyard, patiently waiting to be found. This brings us to a tiny, icy world with a spooky nickname and an orbit that defies belief: a dwarf planet known as the Goblin. Its official designation is 2015 TG387, but it earned its Halloween-worthy moniker because it was first spotted around that holiday in 2015 by astronomers using the Subaru telescope in Hawaii. At the time of its discovery, it was nearly 80 astronomical units from the Sun. That's 80 times farther out than Earth is, a realm so distant that the Sun would appear as little more than an exceptionally bright star in a pitch-black sky. But the Goblin's distance wasn't its most shocking feature. It was the bizarre, stretched-out path it takes around the Sun. This isn't a nice, neat, nearly circular orbit like the planets. The Goblin's orbit is incredibly elongated, a skinny ellipse that takes it on a journey of staggering proportions. At its closest approach to the Sun, its perihelion, it's still a remote 65 astronomical units away, far beyond Pluto. But then it swings outward on its monumental journey, reaching an aphelion, its farthest point, of an almost unbelievable 2,300 astronomical units. A single orbit for this tiny world takes an astounding 40,000 years to complete. To put that in perspective, the last time the Goblin was at its current position in the inner solar system, much of humanity was still living in caves during the last ice age. This kind of object is known as an extreme trans-Neptunian object, or ETNO, and its existence alone is fascinating. But the Goblin isn't just a curiosity, it's a clue, and it's pointing towards something much, much larger. The profound mystery of the Goblin, and a handful of other objects like it with similarly odd clustered orbits, is that they shouldn't exist in their current configuration. According to our understanding of the solar system's gravitational dynamics, the orbits of these small, distant bodies should be randomly oriented, their paths scattered in all different directions by the combined gravitational tugs of the known giant planets, Neptune in particular. But they aren't. Instead, the perihelia of these objects, their closest points to the Sun, are mysteriously clustered together in space. It's as if an unseen shepherd is herding them, keeping their orbits aligned and preventing them from spreading out. This peculiar clustering is a statistical anomaly so significant that it cannot be mere coincidence. There must be a gravitational influence, a massive one, that we haven't yet accounted for. This is where the hypothesis of Planet 9 comes in. First proposed by astronomers Konstantin Batygin and Mike Brown at Caltech, Planet 9 is a theoretical world estimated to be about 5 to 10 times the mass of Earth, orbiting the Sun on a highly inclined path hundreds of times farther out than Neptune. The gravity of such a colossal object, the argument goes, would be more than enough to sculpt the orbits of these distant dwarf planets. It would act as a persistent, dominant force in the outer solar system, shepherding the perihelia of objects like the Goblin into the same region of space and giving their orbits the same peculiar tilt. The Goblin's orbit is precisely what the Planet 9 model predicted. Its discovery didn't just add another data point, it provided a powerful statistical validation, making the case for the hidden planet stronger than ever before. Each new object found on this strange, shepherded path increases our confidence that we're not just seeing patterns in the noise, we're seeing the gravitational fingerprint of a true planetary master. The search for Planet 9 is now one of astronomy's most thrilling detective stories. Telescopes around the world and in space are scanning the predicted regions of its potential orbit, a painstaking process of looking for a single, faint, slow-moving dot against a backdrop of millions of stars. Finding it will be monumentally difficult as it would be incredibly dim, reflecting only the tiniest fraction of the Sun's distant light. But the potential reward is a transformation of our understanding of the solar system's architecture. The confirmation of Planet 9 would mean our cosmic neighborhood has a true ninth planet after all, one that has eluded us for centuries simply because its orbit is so vast and slow. It would rewrite textbooks and force us to reconsider the formation and evolution of our entire planetary system, suggesting a dramatic past perhaps involving a gravitational upheaval that flung this giant world into the frozen depths. The Goblin, therefore, is far more than just a distant piece of ice. It is a celestial signpost, a tiny messenger from the dark frontier of our solar system whose silent, patient dance is guided by the hand of a giant. Its discovery reminds us that even in our own celestial backyard, there are profound mysteries left to solve and giant worlds left to find, proving that the age of exploration is far from over. And yet, even as we chart the potential orbits of hidden giants within our solar system, the universe continues to demonstrate its capacity for violence on a scale we are only beginning to comprehend, offering us a front-row seat to a stellar catastrophe through a remarkable trick of cosmic geometry. This brings us to one of the most detailed forensic examinations of a black hole's power ever conducted, a study made possible by a phenomenon known as an X-ray echo. The story begins with a relatively common cosmic event, at least in the grand scheme of things, a tidal disruption event. This occurs when a star, in its endless journey through the galaxy, wanders too close to the immense gravitational pull of a supermassive black hole. The black hole's tidal forces, the difference in gravity between the side of the star closest to the hole and the side farthest away, become so overwhelming that they exceed the star's own gravity, the force that holds it together. In a cataclysm of unimaginable violence, the star is literally ripped apart, stretched into a long, thin stream of superheated gas in a process poetically known as spaghettification. This stream of stellar debris doesn't just vanish. It wraps around the black hole, colliding with itself at tremendous speeds and forming a swirling, incredibly hot accretion disk of plasma. As this material spirals inexorably inward toward the event horizon, it is heated to temperatures of millions of degrees, causing it to glow brilliantly, not in visible light but in high-energy X-rays. This flash of X-rays is the black hole's dinner bell, a brilliant but short-lived signature of its feast. For decades, astronomers have detected these flashes from galaxies millions of light years away, but they were always just that brief, unresolved flashes. We knew a star had been destroyed, but the intricate details of the immediate environment, the physics of the accretion disk itself, remained hidden in the blinding glare. The breakthrough came not from looking directly at the flash, but by listening to its echo. In 2018, a team of astronomers using two X-ray space telescopes, NASA, a Neutron Star Interior Composition Explorer, or NICER, and the European Space Agency's XMM Newton, observed a tidal disruption event in a galaxy called Assassin 14 Li. What set this event apart was that the initial X-ray flare acted like a cosmic flashbulb, illuminating the structures around the black hole. This intense burst of radiation then began to bounce off, or echo, from the clouds of gas and dust that were orbiting the black hole at various distances. It's a process analogous to sonar. A bat emits a chirp and listens for the returning echo to map out its surroundings. In this case, the black hole's meal provided the chirp, and our X-ray telescopes listened intently for the returning echoes. By meticulously analyzing the minute-time delays between the initial flash and these returning echoes, along with subtle changes in the energy signature of the X-rays, astronomers were able to perform a feat of cosmic cartography that was previously thought impossible. They could triangulate the precise location of the gas clouds that were reflecting the light. This allowed them to create a detailed three-dimensional map of the black hole's environment, charting the structure and geometry of the newly formed accretion disk and the distribution of matter around it with unprecedented precision. It was like using the flash of a camera to momentarily illuminate a dark, cavernous room, and then studying the reflected light to deduce the room's exact dimensions and the position of every object within it. The data revealed a dramatic and dynamic scene. The echoes showed that the accretion disk was not a simple, flat frisbee of material as often depicted in simplified models. Instead, it was a warped, irregular structure with its outer regions tilted at a different angle than its inner regions, likely a result of the violent and chaotic way the stellar debris fell inward. Furthermore, the echoes provided direct evidence for the existence of a long-theorized but never directly observed feature, a superheated corona of electrons just above and below the black hole. This corona is thought to be the engine that produces the high-energy X-rays, and the echo data allowed scientists to measure its size and location relative to the black hole and the disk for the very first time. This entire investigation, from the star's destruction to the mapping of its aftermath, unfolded over a period of months, providing a real-time view of how a black hole's feeding apparatus assembles itself and evolves. The echoes transformed a single, blinding flash into a rich, multi-layered symphony of data, each note revealing a new detail about the most extreme gravitational environment known to exist. It demonstrated that we can now move beyond simply detecting these monstrous events to truly performing detailed forensic autopsies on them, using the very light from the destruction to illuminate the architecture of the abyss itself. And in doing so, we are decoding the fundamental physics that governs the final moments of matter in the universe. If mapping the ghostly echoes around a black hole gives us a forensic view of cosmic violence on a stellar scale, our next discovery pulls the camera back to reveal a potential scar on the very fabric of the cosmos itself, a feature so vast and anomalous that it might just be evidence for a reality beyond our own. This is the story of the cosmic microwave background cold spot, a feature that sounds deceptively simple but represents one of the most enduring and profound mysteries in modern cosmology. The cosmic microwave background, or CMB, is our universe's baby picture. It's the faint, cold light that fills all space, the cooled and stretched afterglow of the Big Bang, emitted when the universe was just 380,000 years old. When we map this radiation with satellites like Planck, we expect to see a nearly uniform tapestry with only tiny, random temperature fluctuations, ripples that represent the seeds from which all galaxies, stars, and planets would eventually grow. These fluctuations are tiny, varying by mere millionths of a degree, but there is one region in the constellation Eridanus that breaks all the rules. This is the cold spot. It's not just slightly cooler, it is a massive circular region of space about 1.8 billion light-years across that is significantly and inexplicably colder than the average by about 70 microkelvin. For years, the leading hypothesis was that this chill might not be a primordial feature imprinted at the beginning of time, but something much closer to us. This is the concept of the supervoid. The idea was that between us and the cold spot, there might exist an enormous, underdense region of space, a vast cosmic void where galaxies are few and far between. As light from the CMB travels through such a void, it must climb out of the gravitational well created by the lack of matter. According to general relativity, light loses energy as it climbs out of a gravitational potential, a phenomenon known as the integrated Sachs-Wolf effect. This energy loss would manifest as a slight cooling or redshifting of the CMB light, potentially explaining the cold spot. It was an elegant solution, a cosmic mirage created by a giant hole in the universe's structure. Astronomers began a dedicated search for this proposed supervoid, and indeed they found one. A large underdense region, now called the Eridanus supervoid, was identified in the foreground of the cold spot. The problem: it's simply not enough. The void they found, while large, is not nearly vast or empty enough to account for the profound and specific coldness observed. The calculated energy loss from traversing this void can only explain a small fraction of the temperature drop. The cold spot remains stubbornly, anomalously cold, and the hunt for a conventional explanation has largely reached a dead end. With a simple void explanation failing, cosmologists have been forced to turn to far more exotic and thrilling possibilities. The most radical and captivating theory suggests that the cold spot is not a feature within our universe at all, but rather a bruise, a collision scar from a run-in with another universe. This idea is rooted in the theory of eternal inflation, which proposes that our universe is just one bubble in a vast, ever-expanding multiverse. In this model, new bubble universes are constantly budding off from a larger inflationary background, each with its own unique laws of physics. The theory suggests that if two of these bubble universes had formed very close together in the multiverse, they could have potentially collided while both were still inflating. Such a collision would have been an event of unimaginable energy, but it would have left a distinct imprint on the inner structure of each bubble. For an observer inside one of these universes, the collision would appear as a circular disturbance on the CMB, a region where the energy density is different, manifesting as a large, unusually cold or hot spot. The cold spot in the CMB aligns perfectly with the predicted signature of such a cosmic crash. The implications of this idea are utterly breathtaking. If this theory were proven true, it would be the first empirical evidence for the existence of a multiverse. It would provide a window into a reality beyond our own cosmic horizon, offering tangible proof that our universe is not alone. It would fundamentally reshape our understanding of existence, suggesting that the Big Bang was not a unique beginning but merely one event in an endless metacosmic tapestry of creation. Of course, this remains a highly speculative hypothesis. The scientific community rightly demands extraordinary evidence for such an extraordinary claim, and a single anomalous feature, while compelling, is not yet proof. Other, less dramatic explanations are still being explored, including the possibility of a rare, large-scale sound wave in the primordial plasma, or an unusual form of cosmic texture left over from phase transitions in the early universe. Yet, the multiverse collision theory endures because it is a testable prediction from a well-developed cosmological model. It makes a specific forecast about what we should see, and the cold spot is exactly what was forecasted. This makes it more than just wild speculation. It is a serious scientific proposition that is being actively investigated. The cold spot, therefore, represents the very frontier of cosmology. It is a mystery that forces us to confront the limits of our current models and to dare to consider possibilities that were once confined to the realms of philosophy and science fiction. It stands as a humbling reminder that the greatest discoveries often lie not in confirming what we already suspect, but in diligently investigating the things that simply do not make sense. And just as we contemplate the possibility of evidence from other universes, another recent discovery brings the search for interstellar visitors much closer to home, literally crashing into our own planet. While Oumuamua captured the world's attention in 2017 as the first known interstellar object to pass through our solar system, it turns out we had been visited by another traveler from the distant stars 3 years earlier, and it didn't just fly by, it made contact. This is the story of CNEO's 2014-0108, the first confirmed interstellar meteor to ever strike the Earth. The data initially came from US government satellites, part of a secretive network designed to monitor the sky for nuclear detonations by tracking the infrared signatures of large fireballs. In 2019, then-graduate student Amir Suraj and his renowned advisor, Harvard professor Avi Loeb, were combing through the publicly available CNEO's fireball catalog, searching for objects with unusually high velocities. They were looking for meteors that might be moving too fast to be bound by the sun's gravity, a clear sign of an interstellar origin, and they found one. On January 8, 2014, a meteor about 3 feet wide slammed into the atmosphere over the Pacific Ocean, northeast of Papua New Guinea. Its calculated velocity was a blistering 28 miles per second, or over 100,000 miles per hour. This incredible speed was the key clue. After meticulously calculating its trajectory and accounting for the Earth's own motion and gravitational pull, Suraj and Loeb concluded that this object was moving far too quickly to be orbiting our Sun. It was on a hyperbolic trajectory, proving it originated from far beyond our solar system. Its extreme speed suggested it was composed of something much tougher than a typical, fragile icy comet, likely a rocky or even metallic asteroid. For years, this discovery remained a compelling but unconfirmed hypothesis, as the US Department of Defense classified the exact error margin of the velocity data, citing its value for national security. The scientific community, rightly cautious, had to wait for corroboration. That confirmation finally arrived in April 2022 in a stunning and unexpected way. The US Space Command, in an official letter to NASA, publicly confirmed that the velocity estimate for the 2014 meteor was sufficiently accurate to indicate an interstellar trajectory. This official, governmental validation made CNEO's 2014-0108 not just a candidate, but the first known object from another star system to ever land on Earth, predating Oumuamua's visit by more than 3 years. This reclassification instantly transformed the story from an interesting day to point into a tangible reality, opening up an unprecedented scientific opportunity. Because unlike Oumuamua, which shot past us at a distance of 15 million miles, this interstellar visitor had delivered potential pieces of itself right to our doorstep, scattering fragments across the ocean floor. This realization sparked one of the most ambitious and fascinating scientific expeditions of the modern era. Professor Loeb, driven by the conviction that we should actively seek out physical evidence rather than just observe from afar, launched the Galileo project. Its first major mission, to retrieve fragments of the meteor from the bottom of the Pacific Ocean. In the summer of 2023, his team embarked on a journey to the Calculated Impact Zone, a remote area off the coast of Papua New Guinea. They used a sophisticated sled called a magnetic rake, which was towed behind a ship and dragged along the seafloor, designed to collect tiny metallic spherules, molten droplets that would have been created as the meteor vaporized during its fiery descent. The painstaking work paid off. The team recovered hundreds of tiny, millimeter-sized metallic spheres. Initial analysis revealed a highly unusual composition. These spherules were made of an alloy of iron and magnesium with a very low nickel content, and contain trace elements like beryllium, lanthanum, and uranium in proportions that do not match any known solar system alloys or human-made contaminants. This unique chemical fingerprint, which Loeb's team has dubbed Be-La-You composition, is radically different from the iron meteorites common in our asteroid belt. The strength of the material, inferred from the meteor's observed strength during its atmospheric explosion, also suggests it was tougher than even iron meteorites. These preliminary findings, while still being analyzed and debated by the wider scientific community, point to the tantalizing possibility that we are holding in our hands material forged in a completely different star system, with a geological history utterly alien to our own. The implications of this endeavor stretch far beyond the analysis of a few tiny spheres. This expedition successfully blurred the line between astronomy and planetary science, demonstrating that we are no longer limited to studying interstellar objects from a distance. We can now pursue them, retrieve them, and analyze them in our laboratories. It marks the birth of interstellar archaeology, a new field dedicated to physically collecting and studying pieces of other star systems. If these spherules are indeed confirmed to be from CNEO's 2014-0108, they become invaluable time capsules offering direct insight into the composition and conditions around other stars. They could tell us about the prevalence of certain elements, the types of planetary systems that form, and even the potential for chemistry that might be different from our own. Furthermore, the extreme material strength of the original object fuels the same kind of speculative curiosity that surrounded Oumuamua. Could an object of such toughness and unusual composition be a piece of a larger technological artifact? While this remains the most remote of possibilities, it is this very sense of mystery and the drive to explore the unknown that propels such daring missions. Whether the fragments prove to be a unique natural rock or something even more extraordinary, the recovery effort itself is a monumental achievement. It proves that humanity has reached a point where we can actively hunt for pieces of other worlds, turning our planet from a passive observer of the cosmos into an active participant in the collection of interstellar material. After exploring the violent demise of stars and the echoes they leave around black holes, we now turn our attention to a cosmic phenomenon that is the absolute opposite of dense, violent, or destructive. These are the super-puff planets, and the name alone conjures an image of something utterly delightful and bizarre. Imagine a planet the size of Jupiter, a giant that should be overwhelmingly massive. Now imagine that this colossal world weighs practically nothing. That's the enigma of super puffs. They have the volume of gas giants but the mass of only a few Earths, giving them densities so astonishingly low that they are comparable to cotton candy or styrofoam. If you could find an ocean large enough, a super puff wouldn't sink, it would float. This defies everything we know about planet formation and presents one of the most charming and perplexing puzzles in modern exoplanet science. The Kepler Space Telescope was the first to uncover these oddities, spotting them in systems like Kepler 51, which boasts not one but three of these fluffy worlds. The primary method of discovery is the transit technique, where a planet passes in front of its star, causing a telltale dip in starlight. The depth of that dip reveals the planet's size. To determine its mass, astronomers use a different method, measuring the subtle wobble the planet's gravity induces in its host star, known as the radial velocity method. For super puffs, this is where the mystery deepens. The transit reveals a planet with a huge radius, suggesting a giant, but the radial velocity measurements show a minuscule mass, indicating a featherweight. When you crunch the numbers, the resulting density is so absurdly low that it challenges our fundamental models of what a planet can be. So, what exactly are these worlds? How does a planet become so inflated without simply flying apart? Astronomers have developed several fascinating theories, each more creative than the last. One leading idea suggests that these planets are not solid worlds with puffy atmospheres, but rather something more like a planetary embryo, a large rocky or icy core that formed very far out in its protoplanetary disk, where it was able to quickly gather a massive envelope of lightweight hydrogen and helium gas before the disk dissipated. But this alone isn't enough to explain the extreme fluffiness. The true secret might lie in their youth and their location. Many super puffs orbit very close to their stars, and while they might have formed farther out, they migrated inward. This proximity to their star's intense heat could be literally cooking them from the inside out, causing their atmospheres to thermally expand to monstrous proportions, like a cosmic marshmallow held too close to a fire. Another captivating hypothesis ventures into more exotic territory, proposing that we might not be looking at a planet at all, but a planetary system in the making. What if a super puff is actually a rocky planet surrounded by a gigantic, Saturn-like ring system of a scale we can scarcely imagine? If the rings were vast enough, they could block a significant amount of starlight during a transit, making the central object appear much larger than it truly is, perfectly accounting for the strange density calculations. Alternatively, perhaps we are witnessing a planet in its death throes. The intense radiation from its star could be stripping away its atmosphere at a truly catastrophic rate, creating a vast, distended comet-like tail of gas that envelops the planet and makes it appear enormous in our observations. In this scenario, we are catching the super puff at a very brief, tragic moment in its life, a fleeting phase before it completely evaporates, leaving behind only a naked rocky core. The true power of the super puff discovery lies in how it exposes the limitations of our own solar system-centric thinking. We built our models of planetary formation based on the 8 worlds orbiting our sun. But the universe, as it so often does, has shown us that this is merely one possible outcome. Super puffs represent a completely different class of planet, one that doesn't exist here and one we wouldn't have predicted. They are a direct challenge, forcing us to refine our theories and consider new, dynamic processes like extreme atmospheric escape and migration. They remind us that planet formation is not a neat and tidy process but a diverse and often messy affair, capable of producing worlds of breathtaking variety. As we continue to study them with powerful new tools like the James Webb Space Telescope, we will be able to analyze the composition of their atmospheres, looking for the chemical clues that will finally unlock the secret of their incredible lightness. These cotton candy worlds are more than just a curiosity. They are a key to understanding the full, wondrous spectrum of possibilities in the great planetary zoo of the cosmos. But while super puffs represent the lightest and most delicate of worlds, our next discovery catapults us into a realm of cosmic violence and gravitational domination so extreme it has earned a name straight from the natural world's most brutal relationships. These are the Black Widow pulsar systems, celestial arenas where a tiny, spinning corpse of a star methodically devours its companion, offering a front-row seat to some of the most intense physics in the universe. To understand this cosmic predation, we first need to meet the hunter, the millisecond pulsar. Imagine the core of a massive star that has died in a supernova explosion, collapsing into an ultra-dense sphere of neutrons just 12 miles across, yet containing more mass than our entire sun. This neutron star is born spinning rapidly, and it possesses a magnetic field of unimaginable strength. As it spins, it acts like a lighthouse, beaming out intense radiation from its magnetic poles. If one of those beams happens to sweep across Earth, we detect a regular pulse of energy, hence the name pulsar. Over millions of years, a pulsar's spin naturally slows down as it radiates energy away. But a millisecond pulsar is a different beast entirely. It's a cosmic vampire that has found a way to steal a new lease on life and spin faster than a kitchen blender, hundreds of times per second. The secret to its incredible speed is its partner. These systems begin as a binary pair, 2 stars orbiting one another. When the more massive one explodes, it can leave behind a neutron star without completely ejecting its companion. If the two stars remain gravitationally bound, the stage is set for a dramatic and protracted act of consumption. The neutron star's immense gravity begins to pull material, primarily hydrogen, from the outer layers of its companion star. This stolen gas doesn't just fall directly onto the pulsar, it spirals inward, forming a spinning disk of superheated plasma called an accretion disk. As this material crashes down onto the pulsar's surface, it transfers an enormous amount of angular momentum, effectively acting like a cosmic crank, spinning the pulsar up to those incredible millisecond speeds. This process of stellar cannibalism transforms an old, slow pulsar into a rejuvenated, hyper-spinning dynamo. But the story doesn't end there. In fact, it enters its most brutal phase. Now operating at peak rotational velocity, the millisecond pulsar becomes a truly monstrous partner. It unleashes a relentless, dual-pronged attack on the star that helped create it. First, its powerful magnetic field channels particles into intense beams of radiation and energetic wind that blast outward. Second, the rapid rotation itself generates a fierce gust of particles flowing from its surface. This combined onslaught of energy, part gamma rays, part particles, bombards the companion star with the force of a perpetual hurricane. The effect is nothing short of evaporation. The pulsar's radiation is so intense that it literally heats the facing side of its companion to the point of boiling away its atmosphere, stripping away material atom by atom and blowing it out into space. In some of the most extreme cases, this process can completely destroy the lower mass companion, leaving the pulsar isolated once more, a lone predator that has consumed its mate, hence the darkly poetic name Black Widow. The companion in this deadly dance is often a brown dwarf, a failed star too small to sustain hydrogen fusion in its core, making it particularly vulnerable to this kind of stellar dismemberment. Observations of these systems reveal a horrifyingly beautiful scene. The side of the brown dwarf permanently facing the pulsar is heated to temperatures of thousands of degrees, while the far side remains relatively cool. This creates a massive temperature gradient that drives violent atmospheric storms across the companion's surface. Furthermore, the entire brown dwarf can become tidally locked and distorted by the pulsar's gravity, stretched into a teardrop shape as it is slowly consumed. The material being evaporated from the companion forms a vast cloud of plasma that envelops the entire binary system, sometimes even eclipsing the pulsar's signal from our view and adding another layer of complexity to observing these cosmic crimes. Yet, for all their violence, Black Widow systems are priceless gifts to science. They are natural laboratories for studying physics under conditions we could never hope to recreate on Earth. The intense gravitational field of the pulsar allows us to test the predictions of general relativity with exquisite precision. The process of accretion teaches us about the behavior of matter at extreme densities. The evaporation process itself helps us understand how stellar atmospheres respond to immense radiation pressure. By studying the subtle changes in the timing of the pulsar's ticks as it moves around its companion, astronomers can precisely measure the masses of both objects, providing crucial data points for understanding the mass limits of neutron stars. Each of these systems is a unique experiment, playing out over millennia and offering a window into the life, death, and afterlife of stars, revealing a universe that is as brutally efficient as it is beautifully complex. Yet while the Black Widow pulsar showcases the destructive power of a single star, our next phenomenon draws us back to the very largest scales of the cosmos, to the ancient light of creation itself, and the subtle ways it is being twisted to reveal the universe's deepest secrets. We are returning to the cosmic microwave background, that pristine snapshot of the infant universe, but this time we are not looking for cold spots or anomalies. Instead, we are learning to read the intricate patterns of its distortions, to see how this primordial light has been gently warped on its 14 billion-year journey to reach our telescopes. This incredibly subtle effect is known as gravitational lensing of the CMB, and it is providing us with something physicists have dreamed of for decades: a map of the distribution of dark matter across almost the entire observable universe. To understand how this works, imagine the CMB as the most distant and uniform backdrop imaginable, a flawless canvas of light. Now, picture all the matter, both the visible galaxies and the vast, invisible scaffolding of dark matter that lies between that backdrop and us. According to Einstein's theory of general relativity, mass warps the fabric of spacetime. This means that as the photons from the CMB travel across the cosmos, their paths are not perfectly straight lines. When they pass near a massive cluster of galaxies or a filament of dark matter, their trajectory is bent ever so slightly by gravity, just as a glass lens bends light. This gravitational lensing effect imprints a barely detectable pattern onto the CMB, a faint smearing or stretching of its temperature fluctuations. The pristine, sharp ripples of the early universe become subtly blurred, and it is in that blurring that we find our treasure map. The monumental challenge, of course, is detecting this effect. The distortions are incredibly minute, measured in microkelvin variations, a fraction of the already tiny fluctuations in the CMB. It is like trying to measure the gentle warping of a vast landscape by observing the subtle bending of a single blade of grass from miles away. Isolating the lensing signal requires exquisitely sensitive telescopes and sophisticated statistical power. The Planck satellite provided the first all-sky map of this lensing potential, but it was the Atacama Cosmology Telescope, or ACT, and the South Pole Telescope, SPT, that truly revolutionized the field. These ground-based observatories, situated in high, dry locations to minimize atmospheric interference, have mapped the CMB with such stunning precision that they can now clearly detect this cosmic warping. By applying complex algorithms to their high-resolution data, cosmologists can essentially run the lensing process in reverse. They can take the distorted pattern we see today and computationally remove the 14 billion years of warping to reconstruct what the CMB looked like at the moment of emission. The difference between the reconstructed, pristine map and the map we actually observe is a direct measure of the total gravitational influence of all the matter that the light encountered along its path. This is where the true magic happens, because ordinary, visible matter simply cannot account for the strength of the gravitational lensing we observe. The majority of this signal must be caused by dark matter. Therefore, the lensing map is not just a map of matter, it is overwhelmingly a map of dark matter. For the first time, we are not inferring the presence of dark matter indirectly by watching how it makes galaxies spin too fast or how it bends the light from a single, distant quasar. We are seeing its gravitational signature painted across the entire sky, etched into the oldest light there is. This allows us to trace the cosmic web of dark matter in 3 dimensions and across cosmic time, from the relatively recent universe all the way back to when the cosmos was only half its current age. We can see how this invisible scaffolding has evolved, how it has clumped together under its own gravity to form the vast filaments and halos that galaxies call home. The implications of this new mapping technique are profound for testing our fundamental models of the cosmos. The lambda-cold dark matter model makes very specific predictions about how dark matter should be distributed and how that distribution should change over time. The lensing of the CMB provides a powerful, independent test of those predictions. Early results are strikingly consistent with the model, giving us renewed confidence that we are on the right track with our understanding of dark matter as a cold, collisionless particle. But the precision of this data is also beginning to place incredibly tight constraints on alternative theories of gravity, like modified Newtonian dynamics or MUND, which seek to explain galactic rotations without invoking dark matter. These theories struggle to account for the specific pattern of gravitational lensing observed across the entire sky. Furthermore, by combining the CMB lensing map with other probes, like the clustering of galaxies, we can perform new tests on the nature of dark energy and the overall geometry of the universe. This single, subtle distortion in the ancient afterglow of the Big Bang has become one of our most powerful tools for cosmology, a universal scale that weighs the invisible contents of the cosmos and confirms that the dark framework we theorized is not just real, but is precisely where and how we predicted it would be, shaping the universe from the shadows since the very beginning. Imagine a galaxy that has experienced a cosmic heart attack, a burst of energy so intense that it left the entire system glowing with a singular, ethereal hue. This is the story of the green bean galaxies, some of the universe's rarest and most ephemeral objects, acting as ghostly monuments to a cataclysm that briefly flared and then vanished. The tale begins not with the galaxy itself, but with the sleeping giant at its center, a supermassive black hole. For most of its life, this black hole may have been quiet, but for a brief period, a mere 100,000 years in cosmic terms, it awoke with a vengeance, entering a phase known as a quasar. During this active period, the black hole fed voraciously on surrounding gas, and in the process, it became the most luminous object in the universe, unleashing a torrent of high-energy radiation that flooded the entire galaxy. This is where the magic happens. The intense ultraviolet and X-ray radiation from the quasar does something extraordinary. It ionizes the oxygen atoms throughout the galaxy's vast reservoirs of interstellar gas. When an oxygen atom is ionized, it loses an electron, and when that electron eventually recombines with another atom, it releases a very specific wavelength of green light. This is the same process that creates the beautiful glow of an aurora here on Earth, but on a scale that is almost incomprehensible. An entire galaxy, tens of thousands of light years across, shining with a uniform, brilliant green light. This is the signature of a green bean. They were first discovered accidentally by citizen scientists participating in the Galaxy Zoo project, who were scanning through thousands of images from the Sloan Digital Sky Survey and noticed these strange, fuzzy, and unmistakably green objects that didn't fit into any known category. What makes green beans so precious to astronomers is their incredible rarity and the fact that they represent a fossil record of a quasar's power. The active quasar phase is incredibly short-lived. Eventually, the black hole consumes all the readily available fuel in its immediate vicinity, or perhaps the intense radiation pressure blows away the remaining gas and the engine shuts down. The brilliant quasar vanishes, leaving behind a dormant black hole. However, the light from that past eruption takes time to travel. The galaxy's interstellar gas is so vast that the wave of ionization sweeps through it at the speed of light. By the time the central quasar has already faded to a whisper, the galaxy itself is still responding, still glowing from the delayed echo of that ancient outburst. This means when we look at a green bean, we are not seeing the quasar itself. We are seeing the aftermath, the lingering glow from a brilliant flash that has already ended. It is like seeing the ghost of the quasar, a perfect fossilized snapshot of its most powerful moment. This unique property makes green beans invaluable cosmic laboratories. They allow us to study the profound impact a quasar has on its host galaxy long after the central engine has gone quiet. This process, known as feedback, is a critical piece of the galaxy evolution puzzle. Quasars are thought to regulate star formation by heating up or blowing away the cold gas that would otherwise collapse to form new stars. A green bean lets us see this feedback process frozen in time, revealing how the furious energy from a black hole can shape the destiny of an entire galaxy, effectively shutting down its ability to create new stars and sealing its fate as an aging, red and dead system. By studying the size and intensity of the glowing region in a green bean, astronomers can effectively measure the total energy output of the past quasar eruption, something that is impossible to do once the central engine has faded. These celestial green ghosts are therefore more than just a curiosity. They are a direct window into the most violent and influential phases of a supermassive black hole's life, offering a unique opportunity to understand how these dark engines at the hearts of galaxies can, for a brief moment, become the most powerful forces in the universe, governing the growth and death of the very galaxy they call home. And this is precisely why the green bean phase is so tantalizingly brief, and why these celestial ghosts are such high-priority targets for the next generation of astronomical observatories. While the Sloan Digital Sky Survey gave us that first, breathtaking glimpse of their existence, it was like seeing a distant green lighthouse through a thick fog. We knew something extraordinary was there, but the details were blurred. Now, with instruments like the James Webb Space Telescope and the upcoming Extremely Large Telescope, we are essentially building the ultimate cosmic microscopes, tools with the resolution and sensitivity to dissect these galaxies and understand the precise mechanics of the feedback loop that shapes the entire universe. The James Webb Space Telescope, with its unparalleled infrared capabilities, is perfectly suited to peer deep into the hearts of green bean galaxies. Remember, that wave of ionization is a transient event. It's still traveling outward through the galaxy's reservoir of gas. JWST can perform a kind of cosmic tomography, mapping the ionization front in 3 dimensions. By analyzing the spectrum of light across different parts of the galaxy, astronomers can determine where the ionization is most recent and strongest, and where it has already passed through and begun to fade. This allows us to essentially rewind the tape and measure the total energy output of the quasar eruption that started it all. It's like examining the blast pattern from a long-concluded explosion to calculate the precise strength of the bomb. Furthermore, JWST infrared eyes can pierce through any lingering dust that might obscure our view, searching for the faint, telltale signature of the now dormant supermassive black hole itself, allowing us to weigh it and understand its properties now that its brilliant feast is over. But the real game changer will be the Extremely Large Telescope, or ELT, currently being built in the high deserts of Chile. With a primary mirror nearly 40 meters across, this behemoth will offer an angular resolution unlike anything we have ever possessed. Where JWST gives us a stunning global view, the ELT will allow us to zoom in on individual regions within a green bean galaxy. Imagine being able to see the actual interface where the quasar's radiation shockwave is slamming into a cold cloud of molecular gas, the very raw material for new stars. We could watch in real time across cosmic distances as the intense radiation heats that gas, preventing it from collapsing under its own gravity and thus quenching star formation. The ELT could potentially even trace the vast outflows of material that were likely blown out of the galaxy by the quasar's winds, measuring their velocity and composition to understand how these events literally expel the future building blocks of stars into the intergalactic void. The ultimate goal of studying these rare green objects is to solve one of the most pressing mysteries in modern astrophysics, the co-evolution of galaxies and their central black holes. For decades, astronomers have noticed a surprising and seemingly implausible correlation. The more massive a galaxy is, the more massive its central black hole tends to be. This is deeply counterintuitive. How can an object weighing a few million suns, hidden away in the very center of a galaxy, possibly know about or influence the growth of a system hundreds of billions of times larger that surrounds it? The green bean, in its perfect frozen state, is the missing link. It captures the precise moment when the black hole's energy actively dominates the entire galaxy, regulating its growth. By studying this feedback process in exquisite detail, we can finally create unified models that show how a black hole's explosive growth phase can pour energy back into its surroundings, shutting down its own fuel supply and simultaneously preventing the entire galaxy from growing any larger. These rare green galaxies are therefore not just fossils of a past explosion. They are the Rosetta Stone for translating the complex dialogue between a galaxy and its dark, powerful heart, a conversation that ultimately determines the fate of all the stars and worlds that may lie within it. From the fleeting green ghost of a galaxy to the silent, gravitational whisper of a hidden planet in our own solar system, the journey through these 25 discoveries reveals a universe that is infinitely more strange, more violent, and more wonderfully bizarre than we could have ever imagined just a few decades ago. We've stood at the edge of a black hole's abyss and held in our hands the potential fragments of another star system. We've mapped the invisible dark matter scaffolding of the entire cosmos and listened for the echo of a collision with another universe. Each of these phenomena, whether a potential sign of life on a hellish world or the mind-bending architecture of the cosmic web, represents a fundamental shift in our understanding. They are not just footnotes in a textbook, they are the headlines of a living, breathing story of exploration that is being written in real time. What ties these discoveries together is not just their ability to shock and awe, but their profound power to push the boundaries of human knowledge. Every single one, from the solved to the utterly mysterious, acts as a catalyst. The Hubble tension isn't just a disagreement between numbers, it's a crisis that is actively forcing us to invent new physics. The cow wasn't just a weird explosion. It created an entirely new classification of celestial events and showed us we were missing a whole chapter on how stars die. Even the ones that remain stubbornly unexplained, like the WOW signal or the true nature of Oumuamua, are not failures. They are the most exciting results of all because they are the open questions, the invitations for the next generation of scientists to pick up the torch. They prove that our curiosity is our greatest instrument and that the universe is always ready to reward it with a new puzzle. This incredible diversity, from the microscopic scale of a neutrino to the macroscopic horror of the Boötes void, shows us that the cosmos operates on every level simultaneously. There is no single key to understanding the universe. Instead, we must become fluent in the language of gravity, the poetry of light, and the subtle whispers of particles that barely interact with anything at all. The story of modern astronomy is the story of learning to listen to all of these messages at once, to become multilingual in the dialects of the cosmos. It's a messy, complicated, and beautifully interconnected pursuit. So as we reach the end of this particular journey, the most important takeaway is not a list of facts, but an invitation to a state of mind. The greatest discovery of all is the realization that we are living in a golden age of exploration, not defined by ships sailing to unknown lands, but by telescopes and algorithms piercing the veil of the unknown. The next great space mystery is out there right now, waiting for its signal to be recognized, its pattern to be decoded. It might be hiding in the next data dump from the James Webb Space Telescope, in the next alert from a gravitational wave observatory, or even in the observations of an amateur astronomer gazing up at the night sky. The universe has shown us it is capable of anything, and that means our potential for wonder is infinite. Stay curious because the next chapter is already being written, and it promises to be more incredible than the last.